Okay, any questions? So I have about 3 minutes left, unless you want me to go over. I can go over about like maybe 5-10 minutes, and then I can finish the subject. What do you guys say?
I'm okay with it.
Everyone else?
Yeah, I'm fine with it.
Sir, you may continue.
Okay, thank you very much. Okay, so let's look at the highest possible value of m. The highest possible value of m. Okay, assume that this is L. Okay, so the state with the highest possible value of m is alpha L, and if I try to increase that value of L, what should happen? It should give me 0. Okay, so this state is called the maximal weight state or highest weight state. Doesn't matter what it's called. Now let's consider alpha L. So again, it's the maximum, it's the highest weight state. So let's call this the highest weight state. I always misspell highest. Highest weight state. So if I take the highest weight state and sandwich J plus J minus, then we can use the commutation relationship J plus J minus is equal to 2 J3. And then on the right-hand side, I will get alpha L, J minus J plus alpha L plus 2 alpha L, J3 alpha L. But of course, J plus acting on this thing gives me 0, and J minus acting on this thing will also give me 0. So the first term is 0. J3 acting on this is just going to give me L, and then the rest of the thing will be 1. So I get 2L on the right-hand side. And over here, this action, this will lower L to L minus 1, and this J plus will also lower L to L minus 1. And therefore, on the left-hand side, I will get dl minus 1 mod squared is equal to 2L. Now, because dl minus 1 is complex conjugation of CL, I can choose CL to be square root of 2L. So there's an arbitrary choice of phase I'm making. I'm choosing it to be a real number, okay? So this is the one of the values of the constant. So, and now we got this from the highest weight state, but let's consider the non-highest weight states. So suppose that J plus acting on alpha of m is not 0. So m is not equals to L. So if I take such a state and do the same, try to evaluate the same quantity as above, then the first term on the right, this guy, this term is not going to vanish. Here, this was 0. It's going to be non-zero, and so this is going to be alpha m, and then I will have J minus J plus, and then plus of 2 J3, and then alpha m. And if I use my assumptions about this being an eigenvector of J3 and the definition of C's, then I'm going to get, here I'm going to get another C, and here I'm going to get C. So in the end, when the dust settles, just a couple of lines of algebra, I'm going to get an equation which is a recursion relationship for C's. Okay, so I'm going to get this relationship. So if I know CL, so if I set m plus 1 equals to L, and I know what CL is, then using this recursion relationship, I can find all the other values of C, right? That's what the recursion relationships are good for. If you know the boundary value or one of the values, then you can just find out all the other values. Fantastic. So we know that C of L is square root of 2L. Then plugging that into this equation, I get C L minus 1 whole squared is going to be it's going to be m is going to be L minus 1, so it's going to be 2 L minus 1, and this thing we know is square root of 2L, so the square will give me just 2L, so I'll have plus of 2L. So this I can write as 2 times 2L minus 1. Now using this again, but now using this value, I can work out what CL minus 2 mod squared is. So again, m is going to be 2 times 2L minus 1. And sorry, that's the value of CL minus 1. And m is going to be 2 times L minus 2. And then, we can write this in a way that is suggestive, 2 times 3L minus 1 minus 2. Now, suppose that we do this S times. So CL minus S mod squared is, you can find that this is going to be 2 times S plus 1 L, and then minus 1 minus 2 dot 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 minus S. So you get to it by using the lowering operator S times. So that means S is an integer, right? Because it counts the number of times you have used the lowering operator. Integer that counts the number of times J minus has been used on alpha L. Now, this thing is also an arithmetic series. So you can do the arithmetic series and you find CL minus S mod squared is 2 times S plus 1 times L minus half, this is the sum of the arithmetic series, times S plus 1. Or you can simplify it to S plus 1 times 2L minus S. Okay? So now we can write CL minus S to be square root of this thing. Okay? So the ladder must terminate at some point, right? So that means that at some point this thing will be 0. Because that's the only way the ladder can terminate, because S is a positive integer. It just counts the number of times that I've used J minus. So this guy cannot be 0. So this has to be 0. What does that mean? That means there's a value for S, let's call it S prime, such that S prime by 2 is L. Right? So S prime is a positive integer. That means L can be either 0, half, 1, 3 halves, 2, 5 halves, and so forth. So it can be either a positive integer or half of a positive integer. So now recall that L is the highest allowed value of M. L is the highest allowed value of M. And M can only change by 1. That means M has to be either a positive or negative integer multiple of half. If it's an even integer multiple of half, then M is a whole number. If it's an odd integer multiple of half, then it's a fraction. Okay, so now that we have C plus and therefore D, we can now write J plus for a general M. This is L minus M, L plus M plus 1 times alpha M plus 1. And J minus is then alpha of M square root of L minus M plus 1, L plus M, alpha M minus 1, okay? So we see that when M is equal to minus L minus 1, Cm is 0. So that means that if the highest value of M, the highest value of M is plus L, its lowest value of M is minus L. So what does it look like? Examples are such as M can be, say this is the M continuum, not continuum, so discretium. So M can be, say, plus half, it can be minus half. This is one example. The highest value of M can be, say, so this is L and this is minus L. The highest value of M can be, say, 1, then it can hop down to 0, and then it can go to minus 1. This is another example. Third example is the highest value of M can be, say, 3 halves, then it can hop down to half, and then it can hop down to minus 1, and then minus 3 halves. Remember that M can only change by 1 unit. And then, there are an infinite number of examples. I'm just going to give you 4. L can be, say, 2, and then this can be 1, 0, minus 1, 2. Okay? In other words, M can take 2L plus 1 values. Okay, and the representation is therefore, this is the dimensionality of the representation. There are this many independent state vectors in your Hilbert space. Okay, so last comment, I'm just gonna, bring everything together in a picture. And so suppose that you have your maximal weight state, highest weight state. If you apply on it J plus, you get 0. If you apply, say, J minus on it, then you get to alpha L minus 1. But if you apply it, so this is J minus, but if you apply J plus on this guy, then you get to the highest weight state. And then you can go down the ladder by applying J minus and go up the ladder J plus, dot, 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 dot. And then at some point you arrive at the state which is alpha minus L plus 1, and if you apply J minus to it, you get alpha minus L, and if you apply J plus to it, you get back to this thing. But if you apply J minus to it again, you get 0. Okay, so and this is the ladder. Okay, sorry, the picture here is not very good, but I will redraw the picture in the lecture notes. So this is the ladder, and the ladder operators take you up and down the ladder. Okay, so let's stop here. Sorry, I will of course review a lot of this in the next lecture, and you know, take questions. But any questions now? Quick questions.
I kind of just lost track after the L part.
After the L part? Okay, so then you need to like redo this, and I will post the lecture. So work through the lecture, okay? Because the lecture is very, very, you know, it's like a derivation. So all of this is supposed to be new. This is not supposed to be things you know already.
Yeah. So like this whole lecture, like what are we trying to do here with the J?
We are trying to find out what are the states, what are the eigenstates of J3 and J squared.
Oh, I see.
And those are essentially the possible values of M. So we found that the possible values of M are M take 2 L plus 1 values, where L is some positive integer or positive half integer. So that's something you have to choose. Once you've chosen that, the number of values that M can take is given by 2L plus 1. And that value starts from positive L and decreases by 1 down to negative L. So if L is an integer, positive integer, this is an odd number, and it's an odd dimensional representation. But if L is a half integer, positive half integer, then this tells you this is an even number. So then you have an even number representation. In the next lecture, we'll actually work out what these matrices are, what the representation look like.
Okay, sir. Yeah, got it.
Okay, but in the next tutorial, you will be working on the position representation of the Schrodinger equation. Okay, any questions? I know that you have a lot, but you know, we'll go over, like, you know, I will post this soon, maybe tonight, and go over it, and you know, and mull over it, and then you know, we can talk about it in the next class. Okay.